Why is the speed of light constant? Why does it matter? Why is time relative and what does it mean? How can you solve the twin paradox? If you want an intuitive introduction to Einstein's famous theory, this video is for you. Hi, I'm a physicist and I often notice that explanations of special relativity skip the crucial step between the speed of light as constant and relativity freaks everyone out. They skip the basics of Einstein's famous theory. So, this is how I wish I'd learned special relativity. We'll uncover the part everyone misses, discover why light speed must stay constant in the first place, and then we will understand the real reason relativity changed everything. After that, even time dilation will be simple to us, because we will build the two basic building blocks of special relativity. And then we'll uncover why the twin paradox is not really a paradox. Einstein said, physics is always the same for you, no matter if you're standing still or cruising along in your very own private jet. If you throw and catch a ball, you see it moving up and down, no matter if you're standing on Earth's ground or on your jet's ground. The ball doesn't go forward or back, nor left or right, since you're such a skilled thrower. You only miss the catch when your troll of a pilot hits the brakes, speed ups or turns. But otherwise, you are very skilled, and you want me to see that. But while watching you in that suddenly see-through airplane of yours, I noticed something strange. I see your ball moving, but not like this, like this. From my perspective, the ball moves to the left, not only up and down. Who is right? Obviously me. I mean, come on. If you're being honest, you can't even tell for sure if you're moving right now or standing still. Standing with your jet on the ground or flying through the air feels the same. It feels the same and you only see this. Because physics is always the same for you as long as you move at a constant speed into one direction. That's a simple version of Einstein's principle of relativity. Physics is always the same for everyone who moves at a constant speed into one direction. Or put differently, your ball always flies in the same way as long as you're not slowing down, speeding up or changing directions. Well, it always flies in the same way from your perspective, but I see that your plane moves to the left, so I know that your ball has to move to the left too. Clearly your see-through plane has gone to your head, because you reply, from my perspective, I'm standing still and you are moving to the right. And indeed, if I throw a ball up and down, you see it moving to the right. Okay, I have to admit I know that the Earth is moving, so I'm not standing still. I simply don't feel any movement, just like you. Actually, there's no such thing as standing still. You can't tell if something is moving or not. You can only tell if something is moving with respect to something else. I see your plane moving relative to me, and you see me moving relative to you. In physics terms, we say velocity is not absolute, but relative. By the way, velocity is not only speed, but it's speed with a direction. And it's changed by slowing down, speeding up, or changing directions. So, I know you have a velocity relative to me, but I can't say I'm still and you are moving. And neither can you. No perspective is better than the other. We see the ball traveling different distances, but none of us is right or wrong. This means there is no true distance. The distance you see depends on your perspective. Distance is relative, but we can understand each other's perspective if we know how we are moving relative to each other. If I measure your velocity from my perspective, I get all relative velocity. With this relative velocity, I can calculate your distances. Great! We've discovered the basics of relativity. But already Newton knew that distances depend on perspective. He was not happy about it. He refused to accept it, even though it followed logically from his own laws. Einstein's relativity was so revolutionary because it combines the fact that distances depend on perspective with the principle of relativity. We've already met a version of this principle of relativity. Physics is always the same for everyone who moves at a constant speed into one direction. So, physics is always the same for everyone who moves at a constant velocity. But physicists don't seem to like easy words, so Einstein actually said, the laws describing how the states of physical systems change are independent of which of two coordinate systems, moving relative to each other with uniform parallel translation, these changes are referred to. What Einstein meant was, the laws of physics don't change based on the perspective. as long as that perspective moves at a constant velocity. Importantly, when I said physics is always the same for everyone, I meant the laws of physics are always the same for everyone. The laws of physics include Maxwell's equations, the foundation of classical electromagnetism. Out of these equations we know that the speed of light has to be constant. If the laws of physics don't change, this constant has to be the same number, no matter who measures it, if that person is moving at a constant velocity. And indeed, every measurement of the speed of light always gives 299,792,458 meters per second, or short, about 300 million meters per second. So what, you say, sick of talking? You go back to your jet and start playing with light instead of a ball. You can't really throw and catch light, but you place light under a mirror, such that the light travels to the mirror, bounces back and returns, similar to the ball. I look at you and just like with the ball, I see a different motion. To you it looks like this. To me it looks like the light travels a longer distance. This is exciting, because we're at the edge of finding out why the speed of light being constant is such a huge deal. Speed is distance over time, or more precisely, distance over the time needed for this distance. So, your speed of light is given by the distance up and down divided by the time passed. I see a longer distance, but I'm supposed to get the same speed, so I have to have a longer time as well. Otherwise, I would get a bigger number for the speed of light. This means that we experience different times. For me, more time passed by. My clock runs faster, yours runs slower. So time is not an absolute quantity anymore. And that's freaking weird. That's why the speed of light being constant is such a huge deal. Because if you combine it with the fact that distances are relative, you find that time is relative too. From different perspectives, we experience different times. This effect becomes stronger the greater the horizontal distance I see. This distance depends on our relative speed. If we're kind of moving the same way, we nearly get the same time. But the faster you're flying past me, the greater the horizontal distance I see, and therefore the longer my time will be, the faster my clock runs. This is time dilation. The faster something moves, the slower its clock runs. Faster movement, less distance, less time. And we can prove it with real experiments. Take two airplanes. One flies from west to east, so it moves with the Earth's rotation. The other one moves from east to west, against Earth rotation. When they meet, they compare their clocks. The plane that flew east was moving faster because its speed and Earth rotation added up, so its clock shows less time has passed. If I know how fast you're flying past me, I can calculate how much time passed for you. The difference in our time depends only on our relative velocity and on the constant speed of light. Great, so less time has passed for you, and when we meet, you're younger than me. But wait, from your perspective, I am moving, so my time should pass slower. So you're younger and I'm younger as well? We've stumbled into a version of the twin paradox, which is actually not a paradox. Before we get into this, let us quickly recap the two building blocks of Einstein's special relativity. The first is the principle of relativity, which results into the fact that the speed of light is constant. Combine it with relative distances and you get relative times. No perspective is better than the other. There is no absolute truth when it comes to distances, times or velocity. They are all relative. But you can link different perspectives if you use the relative velocity. So what is the twin paradox? Take two twins. One flies into space and comes back to see that they are younger than the twin they left behind. That's the twin paradox. Except that this is not the actual paradox. It's not paradoxic that the twins experience different times, since we learned that time is relative. The twin in space moved faster. The faster something moves, the slower its clock runs. So, they stayed younger. We get to the actual paradoxical part of Einstein's thought experiment if we switch perspectives. The twin in space could argue that they did not move. They just entered a spaceship and then the Earth moved away from that spaceship and came back. Then the twin on Earth should be younger. Don't worry, I got you. The twin paradox is not a real paradox. From my perspective, you are moving. Your time passes slower. But if you want to annoy me with that, you have to meet me first. And that's the crucial bit. You have to turn around with your plane to land on Earth. We remember, velocity is not only speed, but it's speed with a direction. And it's changed by slowing down, speeding up, or changing directions. So, you change your velocity by turning around. You are accelerating. This means your velocity is not constant anymore. But the principle of relativity says the laws of physics are always the same for everyone who moves at a constant velocity. So, if you're not moving at a constant velocity, we cannot swap our experiences anymore. You are accelerating, and you feel it. Acceleration is not relative, it's absolute. It can be measured and felt. You feel the takeoff and landing of the plane. You notice every turn the pilot makes. You can't feel if the plane moves at a constant speed, but you do feel the acceleration when your plane turns. Standing on Earth, waiting for you to come back, I don't feel any acceleration. So our situations are not exchangeable. Your motion is physically different from mine. That's why the twin paradox is not a real paradox. Acceleration made your time pass slower. The twin in space had to change its direction to turn around, and they felt this turning around. The twin on Earth did not feel any turning, so the twin on Earth did not accelerate. Physically different motions, not a paradox, because the laws of physics are only always the same for everyone if they move at a constant velocity. Moving at a constant velocity, you always have to experience the longest possible time. If you experience less time than someone else, you were accelerating. Or put differently, there was some force acting on you. If you now want to learn something about general relativity, check out this video. Thanks for watching. Have a wonderful day.